Okay, chapter 35, we'll be talking about interference. It turns out that light waves can interfere much in the same way that mechanical waves could in chapters 15 and 16. So we'll consider how light from two different sources can interfere with each other. Talk very briefly about the intensity of interference patterns. Key concept is going to be interference from thin films. And lastly, how we can use interference to measure extremely small distances. Just kind of some questions to ponder as we go through this chapter is, even though water is colorless, how come we can see nice cool rainbows on them? It turns out it's going to be due to interference. We can also see interference in DVDs when we look at the reflection off of a DVD. Pretty much what we're going to be talking about in this chapter is going to be looking at electromagnetic waves having a wave nature. Chapter 36 will talk about how they have a particle nature. So let's take a look at just kind of what wave fronts look like again as a gentle reminder. In chapter 15 and 16 I would have said that suppose we have a rock and it's thrown into a pond and we're looking at wave fronts or crests as they move away from a source. Pretty much we're going to have the same thing. Here we're going to have a light source and it's going to be putting out electromagnetic waves, and we can kind of track the leading edge of, say, an electric field crest as it moves away from the source. Crest to crest distance is going to be called the wavelength, and the direction that the waves are traveling in are kind of represented by these green arrows, so always directly away from the source. Much like in chapters 15 and 16, we can say that the wave's speed is going to be the frequency multiplied by wavelength, and here the speed is going to be the speed of light, 3 times 10 to the 8th meters per second in a vacuum. The key to interference is going to be this superposition principle that says first we can treat electromagnetic waves as a sinusoidal wave, or written as a sine or a cosine, and where these two waves are going to overlap, the resultant displacement is going to be the sum of the displacement of each individual wave. We can kind of restate the superposition principle and talk about constructive and destructive interference. If you kind of think about if I have two waves, a wave like this and a wave also like this, and I add those two guys together, then here we're going to have, say, some large positive electric field. Here we're going to have some large positive electric field, large negative electric field, large negative electric field. We're going to essentially add those together and get one very large wave. This is going to be a case of constructive interference. Similarly, if we had a wave kind of like that and we wanted to add it to a wave that was the exact opposite of it, we would just get a straight line or nothing. Now let's take a quick look at if we have, say, 2 point sources. Suppose I have a source on top, S1, and a source on the bottom, S2. And we're going to say that these two sources are coherent, meaning that they're the same frequency, the same speed, the same wavelength, and all that good stuff. Each of these two sources are putting out some wavefronts, some crests, and concentric circles. So we have S1 here and S2 right there. Now let's take a look at where these wavefronts are going to meet up. They're going to interfere with each other. You kind of take a look at point B right here. Point B, you can see that we have a crest from the green one and a crest from the blue one, so those crests are going to line up. One thing that is different about these two, about point B, is source 1 has traveled this distance right here, which is shorter than the distance traveled between short 2, so there's some difference in path length between those two. Part number C is a little bit harder to see. We have still source 1 and source 2 having different path lengths, but now we don't have crests lining up and troughs lining up. Part number C is actually going to be where a crest is going to meet up with a trough, so we're going to have destructive interference. If this was kind of a mechanical water wave, you kind of see right here these rays coming out where it looks like there's no movement. You can also kind of see that moving radial away from the source right here. So let's take a quick look at point B right here. point B, you can kind of see that this distance that the wave has traveled is going to be 7 full wavelengths, keeping in mind that a wavelength is one full cycle of the wave, so the wave's going through 1, 2, 3, 4, 5, 6, 7 full wavelengths from source number 1. Source number 2 has gone through 9 full wavelengths, and there's some difference in this path length between them, which you can see is going to be 2 wavelengths. Now, it turns out that these 2 waves, you can kind of see them meeting up in phase right here at point B, where we're going to have crests lining up and troughs lining up. It doesn't really matter that the source 1 has gone 7 full wavelengths and the source 2 has gone 9 full wavelengths. What matters is the crests line up and the troughs line up. So this difference in path length is going to be an integer number of wavelengths. So it's going to be a multiple. M is going to be 0, 1, 2, 3, or 4. Now taking a look at point C. Now point C, there's a path length difference. From source 1, it's gone 9 3/4 wavelength. From source 2, it's gone 7 1/4 wavelength. The difference in path length here is going to be a half, and that half is going to make all the difference between whether the crests line up or the troughs line up. You can kind of see right here that a crest is going to line up with a trough, and there's going to be perfect destructive interference. So this difference in path length is going to be an integer half integral number of wavelengths. So M is going to be 0, 1, 2, but the difference in path length has a half added to it, and so it's going to be 1/2 of wavelength, 1.5 wavelength, 2.5 wavelength. So these waves are going to cancel each other out. And this is going to be true for not only mechanical waves, but also electromagnetic waves. So let's see how we can have constructive and destructive interference with light. We're going to talk about a very famous experiment by Thomas Young in 1800 that just demonstrated the wave nature of light. And I'm going to be referring to this experiment quite a bit in the next couple of chapters, so make sure you understand how it works. First, we're going to have monochromatic or single wavelength light kind of coming directly into a slit. This would be laser light nowadays. This slit right here is going to behave as a point source, and it's going to send out kind of coherent waves, wavefronts like that. And these wavefronts are going to travel the same exact distance to two slits on another sheet, and this is going to be 2 coherent sources. Remember Huygens principle that says we treat each wavefront as its own source. So here we're going to have 2 sources now, because we've treated that wavefront as a source and that wavefront as a source, and so we can get wavefronts that are interfering with each other. And what's going to happen is we're going to set up a nice little sheet of paper right here, and we're going to see regions where there's constructive interference, there, and there. And then there's going to be regions of destructive interference here, here, and here. Now let's kind of take a look at the geometry of this guy. Here we have some screen that's some distance r away, and we have this point that we're interested at, and this is some distance y away from the normal line, straight between the 2 slits. So we have the paths R1 and R2. What we kind of do is we say, well, as long as R is much larger than the slit length, we can treat these 2 paths as being parallel. So this angle that this ray makes is going to be roughly the same as that angle right there. Now we can say, well, look at this. The path length difference is just going to be this distance right there, which is going to be d sine of theta. So my criterion for destructive interference, R1 minus R2, is going to be d sine of theta, and the same over here. D sine of theta for destructive interference must be m, which is 0, 1, 2, 3, 4, so on and so forth, plus a half multiplied by the wavelength. For constructive interference, d sine of theta is going to be equal to integers m 0, 1, 2, 3 multiplied by the wavelength. Super set of equations right here. Now we can also relate this distance y to some various things and do some geometry, and we can write this distance y is going to be r multiplied by m lambda divided by d, where r is the distance to the screen, d is the separation between the slits, m is an integer, and this is going to be for constructive interference. And we can relate this distance y for destructive interference to be equal to r m plus 1/2 multiplied by wavelength divided by distance. So another super important equation to be able to use. So this is kind of a photograph of what we would see on the far wall. So here we would have our zero line, and we're going to see bands of constructive and destructive interference. Note that m is going to be 0, plus or minus 1, plus or minus 2, plus or minus 3, so on and so forth. So we're going to first start off with constructive interference. M is going to be 0 here. So at that point, ym is equal to 0. We're going to have a bright band. It's actually going to be the brightest band. And then m is going to be plus 1, plus 2, plus 3, plus 4. So we're going to have regions of constructive interference. And then at the half integer wavelengths, m is equal to 1/2, 3/2, 5/2, 7/2. Then we're going to meet the criterion for destructive interference. So my regions for y is all going to be kind of coming from this line in the center. This line in the center is actually going to be the brightest band. The intensity is going to die off as we get further and further away from it. And the direction doesn't matter. M can be equal to -1, -2, -3, and so on and so forth. So let's take a quick example. We're going to follow example 35.1 here, where it tells us the distance of separation for the slits, 0.2 millimeters. Distance to the screen, 1 meter. I'm looking at the third brightest band, and I'm told that third brightest band is about 10 millimeters up. So I've gone ahead and written that, and we're interested in the wavelength. So we're very simply going to rearrange this expression for wavelength, and pretty much just get it all into the right into the metric system. So ym is going to be 9.49 times 10 to the third meters. Distance for the slits, 0.2 times 10 to the minus third meters. Distance to the screen is going to be 1 meter, and I'm looking at the third band, and so this wavelength of light is going to be 633 times 10 to the minus 9th meters, or 633 nanometers. And let's very briefly take a look at example 35.2 to look at the broadcast pattern of a radio station. This is essentially going to have two sources that are broadcasting on the same frequency, and these guys are 400 meters apart, and we're going to see for m equals 0, the angle is going to be equal to 0. For m is equal to plus or minus 1, the angle is plus or minus 30. You can see that along this region right here, there's always going to be constructive interference. If you've ever wondered why truckers have dualies for their CB antennas, it's because they want to broadcast in the forward and backwards direction. Let's just kind of pick this guy right here and figure out what our wavelength of the radio station is equal to. That guy is going to be equal to d sine theta divided by m. So here we're going to have 400 meters multiplied by sine 30. Divide that by 1. Sine of 30 is 1/2. So we're going to have 200 meter long wavelength, or 200 meter long wavelength for this radio station.